Testing 1, 2. Houston, this is Apollo 13. We are seeing some unknown lights outside the window. Oh, yes. We have audio. So, let's see here. Bedini Tesla switch. Having a second look. Third look. Let's see here. Okay. That's your signal generator. Just going to go briefly over this and how I understand it. And I'm going to play 10, 20 minutes of energy from the vacuum series, gracefully shared by Davey Oneness. So he says use a 2N3055H because it can handle more amps. He says it's bigger piece, so it has more amps to handle. And so this is like switching DC power and dumping potential rapidly from one side to the other, from what I understand, from these two 12 volts. You know, they're in series, okay? But when you take their parallel points, they're in series, right? So you double the voltage to 24, and you have positive 24 on this end, and negative 24 on this end. Going across the positive of this 12-volt battery, the negative and the positive. That's positive. So yeah, you're going to be able to push potential over to that 12 volt using the 24 volts, which is a higher potential. And looks like he's got a fan here taking advantage of the transfer. And a 3 amp blocking diode. Looks like a blocking diode, I don't know yet. It would block positive from going that way. I guess that's just to, make sure the flow is. Let's see, positive would go this way. Yeah, I don't know why he has that there. But you switch this transistor at a high speed, I guess at a high speed, to influence 24 volts across this battery. And there's your signal generator isolated from the trigger circuit it will send the potential voltage of 5 volts over to this high amp transistor. Again, he says, I guess these are the two types of transistors he recommends, being high amperage. And that's all you need. It's a pretty basic setup. There's nothing complicated here. He's just creating a 24 volt potential from this point and this point, and sending it over to here across the 12 volt battery. I'm sorry, 1.2 volts. Sorry, they're 1.2 volts. My bad. I couldn't read it. These are 1.2 volt batteries, D batteries. Nonetheless, the concept is still the same. So you have a 3 volts instead of 24. You have 3 volts across here, across a 1.2 volt battery, and he's switching it at high speeds. Now let's play a little video. Let's see here. Oh no. Okay. Damn it. You're kidding me. StreamYard won't play the format. Oh, here you go.
This is a series on the Tesla switch. That potentiometer that was in there, and watch the radiant or the negative when I do this. It stays the same, but more. These devices all work, and the 8 ohm side went on this side.
By the way, Davey, if you're watching this, that barcode, I didn't put it there. It's just from the software I used to download this.
Turn this device on, and this light flashed. So just imagine this now with bigger batteries, with field effect transistors or any of the newer devices, with bigger batteries and better currents and better circuits and everything that we have today, right? We could get some real power down here, but it's only going to be the differential power. So I want everybody to understand that. So if you have 12 here, and you have 12 here, and 12 here, you have only 12 to work with, minus the drops. So if you have a 1 volt drop, you have 11 to work with, and 2 to recharge the battery, because you have to be over the battery. And the way you can tell that you're over the battery is you're ending up with 24 volts here when this is on. So that leaves 12. But since the potential is 24, it's a little bit higher than what everybody thinks. And the batteries keep climbing upward. So that's the basic switch. That was the basic switch. This was a 2N 5885 originally. And I know what the diagram says because these devices all work. 2N3055H. Not just a 2N3055. It has to be an H device. Now, why do I say H? Because a 2N3055 has a little chip in it like this, and the H device has a chip in it that's about that big in comparison, which means it can handle more current. So there's one of the key things right there. is you want a device that's at least can handle 25 amps. It has big wires and there's not much of a loss. And when we're talking about the diodes, we used high frequency diodes at the time called MR852s. They were 20 kilohertz diodes. 3 amps. Because we thought we were going to be switching up in all these high frequencies, that's the only reason we use that diode. And that's why you see it in the schematic. Today you'll use a Schottky diode with a much lower DCR and much faster cutoff.
DCR being what?
The resistance through the diode, the drop. So we want to keep this drop as low as we can get it. We want to keep it below 0.7 if we can keep it there. So that's basically how the switch operates. You put the pulse in here, this triggers it, and when you look at this with the audio transformer, you're going to look at a spike like that. You know, you're not going to see a perfect square wave on the device. You're going to see something that looks like that, which is just going to instantaneously turn this thing on. So before the actual current can get through the circuit, it's already there. This potential is already over on this side.
Joe, this is the same wave that you
Yes.
showed in all your stuff, isn't it?
Yes, all negative and radiant circuits, they all work the same. There's no way around them. When the radiant goes off the scale, things explode and vaporize. That's what happened to Ronald Brent. So
this has nothing to do with the collapsing coil here?
no,
There is no coil.
has nothing to do with a collapsing coil. It has to do with this instantaneous switch that appears before the current drags this down. And I've drawn that on my internet site. I've always showed you these in graphs on my internet site. And everybody says, well, he talks in riddles, he doesn't. But if you understand what you're looking at, you're going to understand that I'm talking about potentials here. That this is going to become a delta T. And that water's going to flow downhill. It's not going to go uphill. You see? So, you know, there were no riddles on my internet site. It's just the people that went there didn't understand what they were looking at. Oh, that can't possibly work. That isn't the way you do engineering.
So that's the
oh, yes, it is the way you do engineering.
the difference between, if you're not switching that on, you're just leaving them in parallel.
Right.
It's going to be a big difference.
Right, you can turn this on. You could very simply just take this transformer out of here and do what the electrical engineering school is going to teach you to do. And that's just bias this thing on and adjust it with a voltage divider. And there, you can turn your light on, and now you just got a steady current through the whole circuit, and you're just defeating the whole purpose of the switch. Because the idea is to break things up in pulses so that you're not burning the energy constantly in the circuit. You want to turn it off before the current can catch up. And so what we've done is we put a little model together for everybody, and then we'll show it after we just do a little bit more with this.
So 1, 2. So yeah, that's what I see. I see, a simple concept here of creating a higher potential over a lower potential and switching the higher potential over the lower potential. Oops, where is that thing? What the hell? Okay, so it's working. And this can be done with any voltage of batteries you want to use. Just so long as the battery that you're switching the higher potential over has a lower potential. I don't know what to think of this other than, you're just moving amps, because this is not, I don't know. I got to keep listening to this because he has drawn a spike here for some reason. I mean, where is there going to be a spike? This is just a trigger coil. So suppose there is a spike happening and it's coming from the switching right here of the the plus of this battery and the minus of this battery, because that's the emitter, pretty much acts like a diode. So any plus energy that goes in the collector out the emitter would, I guess it would go, it would go this way because of the emitter, the way the emitter's pointing. And then you have this other diode over here, which I think I'm beginning to figure out. He's making sure positive is going that way, positive energy. So that it hits the positive terminal of this battery. And cuts through it. It stops there. It's the weirdest thing. Oh, God. Bedini, what are you doing here? I guess if there is a spike happening, that would mean this positive here would turn into a negative, and this negative would turn into a positive. Maybe there is a spike happening here. I've never built this. So let's say there is. That would explain why he has a 3 amp diode there. Because the spike would go this way through the diode. And deposit itself there. The negative spike it's got 24 here for some reason. I think these are 12-volt batteries. but the negative would have to, I guess, when this closes, it would, cut across here and meet up over there across this battery. Then the spike would, and it would not only that, it would go across that battery in the wrong direction, because that's the positive terminal. So what's going on here? I don't know. I have to watch more of this, but from what I understand so far, it's just taking a greater potential and dropping it over a lower potential at a high-speed switch. That's your trigger signal. I don't understand what this diode is here for. The way it's pointing with these batteries doesn't make a whole lot of sense. Let me see if I can see it in the video.
He wanted S3 to purpose of the switch. Because the idea is to break the instantaneous switch. So that's basically how the switch operates. You put the pulse in here, this triggers it, and when you look at this with the audio transformer, you're going to look at it to work with, minus
Okay,
drops.
he's going to put that
So
diode
if you
in
have
soon.
1 volt drop, you have 11 to work with, and 2 to recharge the battery. Because you have to be over the battery. And the way you can tell that you're over the battery is you're ending up with 24 volts here when this is on. So that leaves 12. But since the potential is 24, it's a little bit higher than what everybody thinks. And the batteries keep climbing upward. So that's the basic switch. That was the basic switch. This was a 2N 5885 originally. And I know what the diagram says because these devices all work. 2N3055H. Not just a 2N3055. It has to be an H device. Now, why do I say H? Because a 2N3055 has a little chip in it like this, and the H device has a chip in it that's about that big.
There's your high amperage.
Which means it can handle more current. So there's one of the key things right there. Is you want a device that's at least can handle 25 amps. It has big wires and there's not much of a loss. And when we're talking about the diodes, we used high frequency diodes at the time called MR852s. They were 20 kilohertz diodes. 3 amps. Because we thought we were going to be switching up in all these high frequencies, that's the only reason we use that diode. And that's why you see it in the schematic. Today you'll use a Schottky diode with a much lower DCR and much faster cutoff.
DCR being what?
The resistance through the diode, the drop. So we want to keep this drop as low as we can get it. We want to keep it below 0.7 if we can keep it there. So that's basically how the switch operates. You put the pulse in here, this triggers it, and when you look at this with the audio transformer, you're going to look at a spike like that.
Okay. So it does spike. And if it spikes, this positive becomes a negative, and the negative becomes a positive. So here you have a positive now, and a negative. So this diode would funnel it through the fan, I guess. And the negative, well, here you go. Okay, here's another route. Negative. Well, let's just say this is positive from flyback, cutting across that battery. And then it's going to hit the positive of this battery, which would be good. I'm not sure what to think about throwing a positive on the negative side of this battery. But that would be kind of a negative charge to the battery, I guess. The positive flyback would hit the positive terminal of this battery. And that's a strange one. The negative, the only way the negative can get over here is when the switch closes. So, starting to see something here. When that switch closes, he connects the two batteries in series and turns creates the higher potential. When the switch opens, then the flyback happens probably on both batteries. Let's just continue for a little bit here. Oh man, I had the wrong screen up. What I'm looking at here is when this switch is open, nothing's happening, right? But when it closes, he connects these two batteries together, creates the higher potential. And then the switch opens again. And that higher potential has to go somewhere. So, and it probably goes somewhere in the form of flyback at that point. From plus to plus onto this battery. And why would there be a positive flyback here? Well, let's find out. Let's say we're energizing these two batteries together. We put this positive over to this negative and influence it with a positive. This positive is already here. God, this is confusing, but I guess once you do the experiment, you see that there's a flyback happening, And right now with the gate open here, you got positive and positive. And you got nothing, no negative yet, until the gate closes. The gate closes. These two positives are already connected. So when the gate is closed, then you connect this negative with this positive. Yeah, it'll take some more research. I'll have to get back to you guys on this, but just commenting.
You're not going to see a perfect square wave on the device. You're going to see something that looks like that. which is just going to instantaneously turn this thing on. So before the actual current can get through the circuit, it's already there. This potential is already over on this side.
Joe, this is the same wave that
Yes.
you've shown in all your stuff, isn't it?
Yes, all negative and radiant circuits, they all work the same. There's no way around them. When the radiant goes off the scale, things explode and vaporize. That's what happened to Ronald Brent. So
this has nothing to do with the collapsing coil here?
no,
There is no coil.
has nothing to do with a collapsing coil. It has to do with this instantaneous switch that appears before the current drags this down. And I've drawn that on my internet site. I've always showed you these in graphs on my internet site. And everybody says, well, he talks in riddles, he doesn't. But if you understand what you're looking at, you're going to understand that I'm talking about potentials here. That this is going to become a delta T. And that water is going to flow downhill. It's not going to go uphill. You see? So, you know, there were no riddles on my internet.
When he says water is going to flow downhill, that cued me in there. So the positive is going to go this way, downhill. And he doesn't want it to go past this diode. He just wants to charge up this battery, right? I don't see how it's going to charge, though, with that diode there. That's the whole thing. Back to the drawing board.
Site. It's just the people that went there didn't understand what they were looking at. Oh, that can't possibly work. That isn't the way you do engineering. That's
So that's the
oh yes, it is the way you do engineering.
the difference between, if you're not switching that on, you're just leaving them in parallel.
Right.
It's going to be a big difference.
Right. You can turn this on. You could very simply just take this transformer out of here and do what the electrical engineering school is going to teach you to do, and that's just bias this thing on and adjust it with a voltage divider. And there, you can turn your light on, and now you just got a steady current through the whole
it's a light.
circuit, and you're just defeating the whole purpose of the switch, because the idea is to break things up
Sub 7.
in pulses, so that you're not burning the energy constantly in the circuit. You want to turn it off before the current can catch up. And so what we've done is we put a little model together for everybody, and then we'll show it after we just do a little bit more with this.
He wants to turn it off before the current can catch up. So, you know, switch is off now, but when the switch is on, the potential is created across these 2 points. Okay, so you turn it on, you create that potential. And still, again, how does the negative potential get across that diode? It's not biased properly. There must be a polarity flip happening here or something.
So anyway, what I've drawn here, and I want to get out of the way of this, I want to actually point, okay, this is the full Tesla switch to work with, minus down to the basics how we switched this. so that you can understand the switch. 5, and this is 1.5. That's 3 volts. By the time here and put a transistor in here, and everybody knows this is going to be backwards because the positive is on the collector if it's an NPN. When you run current
Let
through
me go
here,
back a little bit.
what's left over feeds the motor or the light bulb, and the remainder goes in this battery as a charge. So this battery is always gaining. So now if I flip these, if I had some convenient switching, and I took this battery, moved it here, and moved this battery here, then this battery would be under charge. And if I did the same thing on the other side, it would do the same thing. So
those two center ones are in parallel.
yes. So let's get right to it. Why did everybody have so much trouble with a Tesla switch? Is probably because they didn't understand
That's right.
the circuit.
That's right.
So we're going to call these 5
The road to success is admitting your failures.
volts each.
When it comes to electrical roads, you have to admit you don't understand something before you can understand it.
So here's your plus terminal, here's your minus terminal. Then what you had was you had another battery. The same thing down here. 5 volts. Plus, minus. But the thing that you didn't have with the other arrangement is what we did was we came in here and put a transistor in here. And everybody knows this is going to be backwards because the positive is on the collector if it's an NPN, and the emitter is going to go to the negative. So now if I have these batteries, and I arrange the switches the same. And they're 5 volts each. Okay, so what is it that I need
Remember,
to
you
do
said the emitter goes to the negative.
make the thing switch correctly? Well, you can't just take this side, turn it on, and dump it across this side because it would be open. You have this transistor in the way, right here. So, conveniently, what they did was they put a diode here, and they put a diode here, and the opposite this way on the negative terminals.
Negative
They tie
terminals.
them together. And now all of a sudden when you look at this, this side is in parallel, so it's just 5 volts. But when this side turns on, it's 10 volts. So what did we just say? We said if it didn't make any difference, if you put the meter in that line and you turn this switch on and this positive flows here, what you have is you have a 5 volt differential here. But it's negative. It's in the negative end. It's in the negative end. So, let's take into account all of it. We're going to lose some voltage here, probably a volt. And when we put the next switch in 510. 510.
Shit.
Now, this side is in parallel, so it's just 5 volts. But when this side turns on, it's 10 volts. So what did we just say? We said if it didn't make any difference, if you put the meter in that line and you turn this switch on, and this positive flows here, what you have is you have a 5-volt differential here. But it's negative.
Right there. You see, it's negative potential. He's shifting the negative potential as well, I think, I'm not going to figure this out tonight, but I will eventually figure out exactly what's the function of that diode. It looks like it's the function of channeling negative energy or negative flyback portion to regulate the flyback and to not go back the other way, and to capture it. But instead of capturing it with the way he does in the SG with the diode facing the positive, he has it the opposite here, the inverse, where he has the cathode facing the positive of the charge battery, the high voltage diode 1N4007. Anode is on the coil end of the flyback, the positive end of the flyback, and the cathode is touching the positive of the charge battery, which is pointing at the charge battery is positive. But in this circuit, he's putting a diode to the other way around, facing the negative. So here, instead of having the cathode facing the positive, you have the cathode facing the negative. So that allows positive flyback to go in the direction towards the negative flyback.
It's in the negative end. It's in the negative end. So, let's take into account all of it. We're going to lose some
well, he
voltage
did
here,
say-
probably a volt.
He did say there's no inductive spike here, but there is the negative, like you said, the negative. He's shifting potentials, so forget about the right, because he had it facing that way. Yeah, I'll get back to you guys on this.
And when we put the next switch in, because we want to isolate these things. And this is, I think, where everybody's getting confused. Remember, we want to switch banks. We want to take the power, we just want to take the differential power from this circuit. And this is a very small value, but just to prove the point, we're going to use the small value. We're not asking for a lot of power here. We're just asking for the explanation of how the Tesla switch works. So, we know we're going to lose a volt here, we're going to lose a volt here, about that. And if you get real efficient devices, you're not going to lose too much. But we found out later on you also needed a switch here. And see, notice now this positive end can go to this collector, and this emitter end can go over here and feed the diode. See? So if I turn this switch on right now, what I have is I have about 3 volts here that I can use, that I can have. Because the rest is feeding across, the battery's only going to take what it wants to take to charge. So I started out with 10, I got 5 there, I end up with 3, and that's enough. When it runs through the load, you only have to be 2 volts over the batteries to charge them. So, now if I did the same thing on this side, and let's start over right here so we can get this clearly the way that we want to do this. If you notice, when this side turns on, that means this transistor turns on here, this transistor turns on here.
Right. It's like you say, Stefan, it's a potential pump, you know, so it creates the higher potential with the two batteries, and that's the actual pump side. So, and he closes the switch to send positive in one direction and tries to open it up before it can make it to the other side of the circuit, which would be the negative side. And if he's able to do that fast enough, no energy is used. But you already started the shift from one end to the other through that one battery. And again, if you can open up the switch before the current gets to the other side of the circuit, which would be the negative side, current leaves out the emitter's positive, you know. And as soon as you open up the switch before the positive meets the negative, you open up the switch, and now the negative, the positive that reached over to meet the negative had to reach across that single battery. And if the switch opens and it has no negative to reach anymore, it should go back to the battery. You know, it's kind of hard to explain, but what he's saying is if you can open the switch before the positive energy gets across the circuit to the other end, then you can use that potential for free, because you need to complete the circuit for there to be loss. The positive has to touch the negative, and you have to have a short or a load or whatever, a load event. A short does that, and just by the positive reaching the negative side of the circuit. As you see here, going through that single battery, the positive of the two series batteries goes through that single battery over to the negative side of the two series batteries. But if you open up the switch before it gets there, it can't complete its cycle, which is fine because it already went through the single battery and charged it up. So even though it didn't complete the cycle, that single battery already went under the influence of a potential shift, of the potential shift. I'm going to do more videos on this.
So all of a sudden, there's 10
when I get a
volts
better understanding.
that's going to want to appear across this 5 volts. Well, if you go back to my original drawing, I showed you that on my internet site. I tried to explain all this to everybody on the internet site. I said, this is what the difference is. So the difference here is 1.5 volts. If this is 1.5 and this is 1.5, that's 3 volts. By the time it goes to this battery, the difference in potential is 1.5 volts.
Because the one on the right is 1.5 volts?
Yes.
Okay.
1.5.
Okay.
But the thing is, what's your load? You see, you can put a load here. You can put some kind of light here. So you have to calculate this load here to work with what you have as potential. Without calculating the exact load, you're never going to charge the batteries. You're going to deplete the batteries. And no, you can't put a capacitor in place of this battery. It's not the same thing. Okay, this is what Tom Beard and I refer to differential.
Let me just say why I think he says you can't put a capacitor there, because he doesn't want to speed up the transfer of potential. He wants the voltage to be 90 degrees ahead of the current. And a capacitor might change that, capacitors are just very quick to charge and discharge. So it just, any speeding up of the potential transfer makes it so that your switch has to move faster and open up the switch before it gets to the other end. He doesn't want I see what he means by open circuit now a little bit more when looking at this circuit that he created. When he keeps saying it, he wants the potential to move to start heading across the circuit through that single battery, but he wants you to open up the switch before it completes its cycle, so you save on energy and you take advantage of the initial action that was taken by the voltage. And since the amperage is 90 degrees behind, if you can open up that switch fast enough or tune it to the right frequency, you're basically never going to be using amperage. You're just going to, yeah.
And potential. And so, no, you cannot put a capacitor here, and no, you cannot put a capacitor here. It's not going to do anything. It's just going to deplete itself and it's going to stop working. All right? So, let's get right down to the basics, how we switch this, so that you can understand the switch. And then we'll get it, we'll do the whole circuit, and we'll show you a running model, and we'll show you it optically coupled, so we made it a little bit easier for you this time. So, what we did with the switches is that
That's right. That's what I'm saying too. The same thing. Pulling down through the battery, pulling the positive, using the higher negative potential on one end to pull the positive down the positive terminal of the single battery, and of course the double positive potential on the other end, already hitting the positive side of the single battery. I'm seeing the same kind of thing going on, but I want to come up with a way to explain it better, where everybody can get it easier and just build upon that concept, because yeah, it's true. If you can switch your switch at the right frequency, and keep your duty cycle probably as short as possible, because you don't want the current to reach the other end. You just want the voltage to go across the circuit and try to beat the 90-degree lag of the current to the other end.
at that time, optocouplers weren't very good, and so actually this transistor would have been in the circuit this direction between the two batteries. Today we have FETs. You could probably do this.
Yeah, I
very
know,
easy with
grammar.
FETs.
I speak 5 languages.
MOSFET,
It's not easy to get them all
field
perfect,
effect transistor.
especially when you don't practice them, or you don't really learn any of them
Okay,
proper.
so now if we put this battery here.
I did horrible in school
So
with
if everybody
with
that's
the English
interested in
course.
the Tesla switch needs to do these simple experiments, they just better do it, because it's the only way you're
I
going
was
to learn.
learning
how
another
this
language
works.
at the same time.
So I don't care where you put your meter.
Not
or your
in
light.
this country though.
That would be the switch. Right now, there's nothing flowing anywhere because we haven't turned this device on. So, how are we going to turn this device on? Well, somebody's going to come and say, well, you could just put a resistor here and bias the base and it turns it on and turns the light on. Wrong. That's not what we're after here.
But I'd love to be corrected on any grammar.
So what we
I'm,
did
I'm trying to get it all right.
Was we took an audio transformer,
Not good with geometry.
the 1K side, and the 8 ohm side went on this side. So that when we took this and put our pulse into this, it turned this device on and this light flashed. So just imagine this now with bigger batteries, with
Yeah,
field effect
my great-grandfather
transistors
spoke
or any
20,
of the newer devices.
20 plus languages before he was 20. He
with
read,
bigger
wrote, and
batteries
spoke in
and
all
better
of them.
currents and better circuits and everything that we have today, right? We can
I
get
met
some real
him
power down here, but it's only going to
when
be
I
the
was 8.
differential power. So I want everybody to understand that. So if you have 12 here, and you have 12 here, and 12 here,
He has a horrible
you
story
have only 12 to work with, minus the
to
drops.
tell that needs to be told.
So if you have
It's
one
got to
volt
do with the
drop,
world wars,
you have 11 to work
Hitler
with,
and all that shit,
and 2 to recharge
and the
battery.
Russians. And he's not
You
Russian
have to be over
or
the battery.
German. He just,
And
His
the
favorite
way you can tell
language.
that you're over
his favorite language of all of them was German. So for that reason, the Russian intelligence were scooping everybody up, turning them into spies.
the batteries, you're ending up with 24 volts here when this is on.
Yeah,
So that leaves 12.
it's not over what they went through. That's all I can say.
But since the potential is 24, it's a little bit higher than what everybody thinks. And the batteries keep climbing upward. So that's the basic switch. That was the basic switch. This was a 2N 5885.
Let's see if we can pick up anything
Here.
from the advanced circuit here. He gets more advanced with it. The concept, anyway.
1D. That potentiometer that here.
Charging of the batteries?
Yes, the better these batteries are going to charge. Back and forth, back and forth. But that does no good unless you can rectify this and charge a capacitor and use the DC. All right? So, I want you to understand the blue dots are the transistors that are going on the left side here. The red dots are
I ain't no
completely
scientist.
off when the blues
I have
are
a science degree, but I
when
wouldn't
the
say I'm a
reds are on,
scientist.
the blues are completely off. So what you're doing is you're sending
Electrical
the
engineer.
potential difference this way and then that way. Back and forth, back and forth, back and forth. So you're actually just trying to keep all these batteries charged in the circuit. And this is the diagram that Ronald Brent presented to me back then. Now, what we want to do is show you that we've drawn this circuit here, and we want you to take a good look at that for a minute. And then we're going to run the machine and show you that it operates exactly like what we're saying on the board here.
Now, this circuit looks, to me personally, I think you can do with a lot less parts. But let's see what we figure out. Which
Okay,
probably
so
won't be
now
much.
now that you've seen the circuit, and I've explained to you that this side here, the blue dots go on, the red dots are off. So that means you're switching the load backwards and forwards. And an easy way to think of that is a rocking pendulum. So here, and we want you to take the left side here. The red dots are completely off when the blues are on. When the reds are on, the blues are completely off. So what you're doing is you're sending the potential difference this way and then that way. Back and forth, back and forth, back and forth. So you're actually just trying to keep all these batteries charged in the circuit. And this is the diagram that Ronald Brent presented to me back then. Now, what we want to do is show you that we've drawn this circuit here, and we want you to take a good look at that for a minute. And then we're going to run the machine and show you that it operates exactly like what we're saying on the board here. Okay, so now that you've seen the circuit, and I've explained to you that this side here, the blue dots go on, the red dots are off. So that means you're switching the load backwards and forwards. And an easy way to think of that is a rocking pendulum. It's that way, and then it's that way. It goes this way and turns these on, and these charge. And then it goes the other direction and turns these on, and the other side charges. And then what you're doing with the negative terminals, remember what I said about the batteries, and I'll go back over that again. I'll put that right here for you, so you can see what this side is doing. So this transistor right here is sending the energy this way. And I'll indicate that by a blue gun. And this transistor here is turning these two on to put them as if you turned on a light switch. And the load, as it flows from this side to this side, you can have the difference in potential and charge the battery. So as soon as the weaker the battery is, the more of the energy it will suck up to charge. So your load would be right here. Between, guess what? The two negative terminals. And you say, well, how could that work? Well, it works. You just build this circuit.
So when it's going the other way,
Well, when it goes the other way,
it's like that inverted? Or
yes,
yeah,
it's the opposite way.
Yeah, okay.
So this is just a depiction of what's going on here. So you don't see the blue dot. The other blue dot would be over here.
It works because between those two negatives, one of the negatives is a lesser negative, if that makes any sense. Because there's no such thing as a negative. It's all just lesser positives. You have the greater positive and the positive that's underneath that positive, 10, 9, 8 volts, so on. So the negative is just a lesser positive. And between the two negative terminals that he says that he put that battery across, it has a positive and a negative, which is really two positives, one greater, one lesser. Or if you want to say they're two negatives, it's still the same thing. They're two potentials, one is greater, one is lesser. That's why it works, because we're thinking plus and minus all day long. If we thought greater and lesser potential and threw out plus and minus, we wouldn't be able to see the circuit moving. So that's why we have to put the plus and minus everywhere.
To let it come to the diodes. See? Right here.
Yeah. So when it goes the other way, it's mirroring.
Differential.
Mirror image of it. And if this is at 0 degrees, the other side is going to be at 180.
Series, parallel, series.
Yes. Okay. So let's run the machine. and show you that there's no trickery here. All right, so anyway, this is the actual machine, and it's running. And remember what I said. What's the negative energy is a constant source. That's indicated by this yellow light right here. That's exactly what you're seeing. You're seeing both sides switch 180 degrees out of phase from each other. And the frequency is adjusted by the potentiometer that was in there. And watch the radiant, or the negative, when I do this.
You just said radiant.
Stays the same, but more, it's constant.
There's no coil in here.
So now those batteries are going upward. Now, let's say we want to look at the AC. So for this, I want to use an analog meter, because I think that the camera can pick this up much better so that you can see the AC. Okay, so what we want to do is you want to be able to see what the difference of potential is. So remember what I said, the power is going to come out of the negative terminals. There it is. Okay, and if we come down here, so what's that, about 4 volts? Remember I said you'd be missing a volt. Okay, so and if we change the frequency, the charge condition shouldn't change too much. It's about the same.
Same thing, yeah.
So see, you can't affect anything with the negative energy. It's constant once the switching occurs, no matter what
So
frequency.
why have different frequencies?
Well, because of the batteries. We didn't know where the batteries were going to be.
Oh, which is most optimum for charging
Yeah,
the batteries?
which is most obstinate, which you could.
Well, thinking about which is more efficient regarding radiant energy collection, a system with an inductor or without. And through this experiment, he has shown that he apparently has seen radiant come out of it from the switching, because it makes sense. He's moving potential. Maybe that's what an inductor does. It moves potential. So maybe that's just all you need to do to generate the radiant inverted polarity spike. So it might, before looking at this again and hearing what he's saying again, probably the 10th time, he might be onto something, because if you're not inducing current into a coil in the circuit, you're not going to have as much of a voltage gain, but you're also going to have no loss in that coil. So the only place that create loss is in one of these 3 components. And of course, whatever loss happens at the switch, which is there anyway, with or without an inductor. This is just your trigger signal. There's no loss there. That's just small, tiny amount of current. It's just for triggering the transistor. This might be a good science project if you want to determine if it's more efficient to induce negative flyback energy with a inductor or without. And I think that's what he was doing here. No inductor. But inside the batteries, there are, conductive plates. So they are inducing voltage. And a magnetic field is probably happening inside the battery when that induction happens through the plates of the battery. The potential is going to try to push current through the elements of the battery, and whatever elements in that battery that are not willing to polarize with that potential will resist. And there will be some of that. Batteries have resistance. And, not all of the ions in the battery are going to be, cooperating with the potential shift. That's probably where this radiant is coming from, because of the, I had a thought the other day, thinking about the superconductors. If you don't have any reluctance in the coil or any type of resistance, do you have any radiant energy if you don't have resistance? And let's say you're pulsing a superconductor, and I don't think you're going to get any pushback, rebound. What are some words? Recoil, racquetball, bounce. No bounce. What are you bouncing off of? There's nothing to bounce off of inside of a superconductor. Everything is cooperating with the current flow, 100%. There's nothing. There's no reluctance. There's no resistance. So, is there any recoil? Is there any bounce? I don't think so. But there's still a magnetic field. And maybe once the magnetic field encounters a secondary external exogenous magnetic field, it might have a form of competition. If the two if let's say, the fields are alike and they're repelling, and they don't want to. One of the fields doesn't want to turn around to stop repelling the other field, and they both fields refuse to turn around to one of them to show the opposite face to essentially stop repelling and now attract. I mean, those circumstances are out there in the astrological realm, planets and whatnot. They're bound to other rotational forces and whatnot, and occasionally you have alike fields that refuse to stop facing each other, and they just pass each other and facing each other, which would cause a lot of problems on those two planets, earthquakes, whatever, or anything caught in the middle of those two planets would be dealing with a lot of problems. But the superconductor doesn't have any resistance, so is there a magnetic field though? Yes. I don't believe you need resistance to have a magnetic field. I believe you just need current flow. You just need electron flow, to be more specific, or you don't want to call them electrons. You just need vibration without any resistance to that vibration, because it's vibration that causes the magnetic field. Okay? If you have resistance to a vibration, you'll have things like heat, recoil, flyback. And that's why it's useful to harness the flyback, as Bedini is doing, because he knows very well that what I'm saying here is that this resistance in the coil, it doesn't have to be wasted in the form of heat. So you can capture it before it turns into heat. And that's what he did with the SG. But in a superconductor, there is no rebound, but there's still a magnetic field because you're still conducting vibration. It's just having the ohms causes the feedback, or I guess the feedback, you know. So what happens is, as your voltage goes up, your current you have a you, your current drops, okay? Because why? Because why does your voltage drop? It drops when you start using power. And when you use power, your current goes up, okay? And as the current goes up, the coil's resistance begins to diminish, and the coil stops resisting and starts allowing the flow. In the beginning of the initial charge of the coil, it resists because it has not yet been polarized to the vibrational orientation of the molecules in the copper. And you take the charge away from the copper, and the molecules of copper want to return to how they were facing before. And that's the whole deal there. It'd be nice to find a way to charge copper at, say, some frequency to keep it polarized. And you could then remove the charge, and well, there you have it. You have a superconductor. It's staying polarized. All the ions in the copper are staying oriented the same angle towards one direction, and that angular arrangement of the ions is established by vibration of the copper. Um, it establishes geometry. The vibration does, so it creates these specific angles to enable current flow to move freely without having to hit walls or cut corners. When you have everything, lined up in angles, like let's say 45s like that, the current can just ride the rails. You got rails now. But that's the basic idea behind polarizing materials, minerals or metals, to then turn them into magnets, essentially, for a brief moment, or permanently if you keep them charged. But as soon as you remove the charge, the coil no longer has polarization, and that tells you that the copper, molecules went back to the position that they were in before they received a potential to align them and have them all face at attention. For, let's say, a bunch of cadets standing in the row doing their attention sign. They're all facing the same way, and whatever. That's the kind of the thing going on inside the copper coil. That alignment enables the energy to flow smoothly. Without that, the energy gets bounced all over the place. And so now you can see where radiant comes in. When you see energy bouncing all over the place, now you can see radiant energy coming into the picture. And radiant energy is pretty much energy that's being bounced back. and the reverse polarity. And quite frankly, it is bouncing back exactly is exactly what it's doing. It's reversing polarity to come back to your circuit. And that's what he means by open circuit, because if you can close the gate and open it before the current meets up with the voltage on the other end of the circuit, then you have an open circuit. I'll say that again. If you can close the gate and open it before the current makes its way and meets up with the voltage on the other end, because the voltage is going to meet the other end of the circuit before the current does. But if you can open up that switch before the current catches up to the voltage, you never really closed the circuit. I was trying to understand what he meant by open circuit. I was getting onto it. I knew it had something to do with the transistor, and that's what it is. It has to do with the transistor being open when it's open. So when it closes, the voltage already shoots across there before the current. It makes it to the other end. The current is lagging behind. It's on its way. But if you can open up that switch before it gets there, you don't use any current. Because to use current, it needs to meet on the other end of the circuit. But you use voltage. You do use the voltage, but not the current. The current didn't make it on time. You opened up the switch before it got there. Now, the current's trying to get there. And it's like, hey, the switch is open. Or I can't get through here. It stops right there. It can't come over here on this side. It has to complete the cycle to make it short itself out and use up its energy. Switch opened up before it can get through. That's it for tonight, guys. I hope that
Get check out. So you
resonated.
want to measure the battery?
I'll let this play a few more minutes.
We go. So you can watch this switch between the one side. We're looking at the blue dots right now.
Okay.
Okay? So what do we see here? You can see it switching. And if we look at the other side, you can see it switching the other direction. Now where does it all end up? It all ends up across the negatives. You can only have the difference in potential. So if you rectify it, what you're going to get is you're going to get the DC here in the cap. And there it is.
Yeah.
See, I'm loading it with this LED. By the way, there's no resistors in line with any of these LEDs.
So that thing about the graphene, the soot from high voltage lines that short out and spark onto metal plates. I don't know if that's graphene, but I'm willing to bet that it has graphene there, And I can tell you when those arcs happen, you're not using a whole lot of copper. Some of it gets melted off, maybe, 30, 40 grams or 100 grams or something, not a whole lot. But a copper pellet inside of I guess, a vacuum chamber where you can then um, send high voltage and a certain amount of current uh, through the copper to have it incinerate into gas form. And if there's carbon in copper, I'm not sure if there is, but if there is, it might convert straight to graphene onto whatever other material you have inside that chamber. It might just, deposit itself on there the same way they do, when they seal metal with, forgot how they do that. They do it with high voltage. I forgot what they call it, but yeah, they just polarize the metal and fill the chamber with the paint in gas form, and it just sticks to the metal. So the same thing, with any material that, like maybe graphite has an incineration point with high voltage and current. It's certain levels of current and voltage. Like a capacitor, you could build it up to that whatever ideal voltage is to incinerate a small piece of graphene inside of not graphene, graphite, which would probably be a better material to try this with. But I'm not saying to just use one material. I mean, you have to start somewhere. Graphite might be a good one. And then you incinerate that graphite with the voltage and the current inside that chamber with let's say a mica sheet plate of something like plastic or whatever you can put in there next to on the bottom so that the gas falls down on the plate. And then you have a plate that's got graphene deposits on there. Or you have, some type of carbon deposit on there that came from a piece of graphite. Whether it's graphene, I don't know. But right, I'm telling you, they're trying to find ways to mass produce graphene layers with chemistry. And I don't know if that's going to work or not. I'm not a chemist per se, so I wouldn't know. But even chemistry is creating voltages, right? It might be more cost effective to do it with chemistry. It might not be. I have no idea, but you want to get the carbon. You could also use sodium hydroxide. Has I know that has carbon in there because from the Kesh coils, Dr. Kesh, he says use sodium hydroxide. And he said that because there's carbon in the hydroxide. And it comes out in nanocarbon form and it deposits on the copper that you put above the sodium hydroxide. You fill a container with a couple inches of water and drop some sodium hydroxide in there, and you have another rack to hold your copper material above the water, so the gas from that reaction hits your material, and that gas has nanocarbon on there. I've done this, and it deposits nanocarbon on the copper, and the copper turns black, just like the soot on the breaker panels. So, sodium hydroxide might be better, I mean, Dr. Cash is a physicist, he's a chemist, I mean, it's probably more efficient than, using high voltage like I'm saying. But, has the high voltage thing been tried, and I know that the sodium hydroxide thing has been tried. I tried it myself. I don't know if it's graphene or not. I can't verify that. But I can tell you that the copper turned black. I didn't give it no fire. was a chemical fire or whatever.
because it's not the normal energy. So what does the battery look like? Well, you can see I've soldered the batteries together. There's nothing hidden there. And if we go to the DC,
And those batteries are what, just for the record? John?
5 volts, they're NiCad batteries. And if we look at the battery, I'll try to get my arm out of the way. DC plus.
Chili. Yeah, that's another
And it
good,
should be
good
just
one.
over 5 volts,
Yeah.
which means that
Some
it's
type of,
charging upward.
You know,
And if you
aqueous
if
solution.
you feel right here, you can feel sort of a little bit of heat to it.
They're 1.2 volt batteries.
Yeah.
This one,
Yeah, they're 1.2 volts.
not 1.5.
Yeah, well, I was only talking about,
Yeah.
right, they're 1.2.
It's funny, you do a little thinking on this graphene thing, and you start to realize, you know, maybe it won't take that long for them to figure it out, you know, with chemistry, and to use a chemistry that's environmentally sound, you know, like sodium and hydrogen. I mean, that's liquid plumber. Sodium and hydrogen. It decomposes into hydrogen and sodium. It's completely biodegradable. There's a lot of things like that. Old school, you know, chemical products that are completely biodegradable, like hydrogen peroxide and copper sulfide. It's, you know, it breaks into copper and sulfur. Uh, you know, I would be careful with the copper sulfide though, because that copper is toxic. The blue stuff. People are drinking. What's that stuff called? Methylene blue. They're just shutting down their detox altogether. They're just shutting down their liver. That's why they feel good. Their liver is what makes you feel bad, because it's the one organ that's working all the time, and it's also cleaning your body. That's why you feel sick. But the chemistry is looking more promising than the electrical route for graphene. I'm just saying that if there is a way to do it with electrolysis, it would be probably cheaper than using chemistry overall, because chemistry requires raw materials, and electricity it's not a raw material, and you cut down on costs right there, and now you just need to buy the plates, and all you need is electricity, and you can do it. Most likely you can do it with electrolysis. Will you be able to do it in bulk and as quickly as chemistry can do it? Well, that depends if you have the money and you're willing to spend it to figure that out. Go ahead. You know, few people have that money. But for now, it's garage work.
So they're way above where they're supposed to be. And so we'll just let that run. Oh, and something interesting, the negative energy, and I sort of want to show this on camera, is if I goof this around a little bit, I got this little radio here. If I set that there and I want to steal this negative energy with these leads, sorry for the mess, but that's the way it is. Just come off these negative terminals. And you can hear it switching.
What
It's
vial?
a
What
DC,
what did you have in there?
but it's
Copper?
running
What was in there? Water?
the DC
Salt?
circuit. So now,
I don't know what you're talking about. This science stuff, you know.
so let's
You're leaving out the raw
see what we can
specifics.
do with it.
Sparkle.
So let's change this. So see, the higher the frequency,
Yeah.
right? You want to get it above that, where I have it.
The GANs
And then
work.
you're getting
If
a
you're talking about
straight,
GANs,
steady DC out. You can power things without affecting the batteries, and I'll show you that. We don't get AM radio too good here. Might help. So let's look at the batteries. Moving around here.
CO2. Oh,
So you can see we're powering our batteries,
yeah, baking soda
and they're staying up there.
The LEDs still.
and vinegar.
Yeah, the LEDs are the same, and we're running the radio off the free energy, or the negative energy in the system.
So how long did that go for?
Quite a while.
But you spend money on baking soda and
Quite a
vinegar.
while until you deplete the battery, until you deplete the.
I mean, that's
nickel
already
cadmium
10 bucks.
Battery.
So where it's charging it.
If you can do it with electricity,
Yeah, you're able to take the differential.
like let's
that the
say
battery
solar
doesn't
panel,
need, and that's free to the radio.
you don't pay nothing. Pay
And
once
you can see here, if I slow it down,
for the solar panel.
I'm in a charge mode.
Just pay
where
for
I've
the
got
plates
big
and
pulses
the
going
raw
back and
materials.
forth. And what you need to do to run equipment with the negative energy is you need to convert.
That's why I don't like chemistry
You
so
need to
much.
convert it into higher
All those other
frequency,
expensive
for what?
materials you gotta buy. Electrolysis is,
See, now those are big pulses going by.
it's a
and
form
that
of
will make
chemistry.
them bigger.
Okay, what I understand, John.
Salt and
is
electrolyte.
that you charge
Yeah,
the
but
batteries. How does
salt
that
costs
work?
money. Electricity
cadmium
is free if you have a solar panel.
Burning them.
Okay, great, just
Degrade.
If you want to mass produce something,
See, I can't. You
to
can't.
make a bunch of
In other
graphene
words,
batteries.
What you want to do is you want to be able to say, I want to listen to my radio. You want it at a high enough frequency where you can take the energy from the circuit without depleting
Once in a
the
while.
circuit.
Right.
So anybody that says to me that the Tesla
Gans of
switch never
CO2.
worked, it's because they didn't understand it, and there were a few mistakes. So once again, take it up.
carbon dioxide.
And I've got it down at a low pulse.
What solid
Because
do
I
you
don't wanna
use
bring
for
it up too
carbon
high because
dioxide?
I can't watch.
Is that aluminum?
I
No.
can't watch while I'm on the blackboard these batteries. But you can see that the radio would straight.
I know
right
aluminum.
out, and
Aluminum
you
has a
can
lot of
do that.
hydrogen.
So those don't need to be LEDs, they can just be diodes.
Yes. And I've used these colors so I could show you across what's across each negative diode. See, because that's where the energy's coming from. The energy's coming from these negative ends.
So could they all be LEDs or just those two at the bottom?
No, they gotta be diodes. It's just you put your LEDs down here at
Copy.
the bottom. And that's just an indicator of it going back and forth. And
Carbon
actually
dioxide.
better than that, you can listen to it here. Because it just takes that difference in
Oh,
potential
great. I'm gonna
and
get
moves it
flagged
back
now.
and forth in these batteries. 5. As I said, this side Okay,
They still have that 80%.
okay, and this side's 8 ohms, that's fine.
So the nano coated copper and the zinc is releasing CO2. Huh. I didn't know that. It's producing CO2, the reaction? What does that tell you? I mean, graphene or nano-coated graphene nano-coated copper in a tube of salt water with another zinc plate, and the electrolysis reaction between the two, whether they're connected with a wire or just by water and salt, because you can do it with or without the wire. They react because they're two potentials now, right? And they're releasing CO2. So it's like good for plants. Copper nanoplate zinc ingot CO2 will form. All graphene type material would only form once in a while, all on its own. Right, so you can take the copper plate and put the graphene on it with the sodium hydroxide. But if you don't put any graphene on there, the reaction takes longer, and the electrolysis is probably making the graphene. You're right. So I see your point. So what you're saying is that is the cheapest way to make graphene, and that would be correct because you don't have to use any chemicals or gases, and you could just put the copper in there with the zinc and wait. It just takes longer. And you said it only forms once in a while, so how dependable would that be for making graphene batteries? You need it to happen every time. So, sodium hydroxide, and you're using just salt. I'm thinking, I see where you're going with this. The economic route, which is the only way to do it in the long run. No matter who comes up with the idea for making graphene, mass producing it, they're going to have upfront costs if they don't do it right, bigger than the next guy, and they're going to fail. Because the person who can do it the cheapest is the one that succeeds. So yeah, I mean, like those big blue drums, those plastic food drums, you could probably, I would just do it like that, put a bunch of, not one plate, but put like, once you figure out, I think it boils down to the chemical solution. It might not be sodium, salt water, sodium chloride water. And you'll get it to figure out CO2, sodium chloride. Sodium hydroxide is very efficient. There's a lot of hydrogen. Maybe if you give the two plates a small charge and kind of turn them into a fuel cell and have them produce hydrogen, and just instead of using sodium chloride, salt, use plain old sodium with no chloride. And then the hydrogen that you're producing by charging the plates with, let's say, 1.5, 2 volts, the hydrogen that comes off into that water sodium solution without the chloride would bond with the sodium and produce sodium hydrogen which is a step closer to sodium hydroxide for free. I wouldn't be surprised if that's how they make it. Sodium hydroxide, that is. They probably make it with electrolysis. I don't know. I'm just making a wild guess at this point, but I don't really research all this stuff. But they probably do make it with sodium hydroxide with some form of electrolysis with sodium and water, getting the oxygen out of the water. So you got water in there. That's another thing. And you got oxygen in that water. Maybe if there's a way to make heavy water, less oxygen, deuterium water, but that stuff's dangerous and expensive. No, is it expensive? I don't know. I don't know. I wouldn't mess around with that stuff. Meaning chloride may be present. Yeah, well, if you're using salt water, there's chloride in there, sodium chloride. And what I'm saying is, Dr. Cash says he uses sodium hydroxide, not sodium chloride, to make nanocarbon deposits on materials. And if you can make the sodium hydroxide yourself in a slower, different way with electrolysis, you won't have to buy the sodium hydroxide, which costs $5-10 for a small bag. You want to make a lot of this graphene and put it on plates all day long, and you don't want to have to buy a bunch of stuff to do it. You want to just be able to, give it some voltage and buy the copper and the zinc and make your own liquid solution. Chlorine, sodium chloride. Chlorine is a different molecule. It's not chloride. They're not the same. Chlorine is not chloride, but sodium hydroxide has no chloride. Just has sodium and hydrogen. 3 hydrogens, I think. I don't know. Graphene, chloride graphene. I'm just trying to follow in the footsteps of a chemist who has a nuclear physics background. And the guy, Dr. Cash here, he ran away from Iran because they were torturing his family because he refused to work in the nuclear weapons program for Iran. He's a peace-loving man, and he doesn't want to be a part of that crap. They actually, it's a family disaster. I'd rather not say it's his story, but he's a very smart man and he knows his stuff. And he suggests using sodium hydroxide to make your nanocarbon, your graphene. Chlorine is dangerous, man. It can kill you. The gas. Posable chlorine present in water. Hence, poolable. What does posable mean? I don't know. Pool water? Yeah, there's the chlorine in the pool water is bad for you too. It's chlorides or whatever. Yeah. The halides. You got chloride, iodide, bromide, fluoride. Only one you want is the iodine or the iodine, not iodide. You got chloride, bromide, fluoride, iodide. You don't really want iodide. You want iodine, but well, that's interesting. I didn't know that you can make the nanocarbon without burning gas or using chemicals and just doing the GANS process by itself, and it forms. That's interesting. that's a good piece of information. And you might want to keep digging into that. Why is it forming? What are you doing? You're using sodium chloride. The chloride, I believe it will oxidize, speed up the oxidation. That's why it kills bacteria. I think because, well, you really have to look at the chloride molecule, see how many oxygens it has, if it has any at all. I'm not sure. I think it does. For instance, sugar is 6 carbons, 12 hydrogens, 6 oxygens. Salt is 1 nitrogen, NaCl, and 1 chloride. Or Na, 1 sodium and 1 chloride. And the more oxygen that's in the molecule, the more oxidizing it would be, I would guess. So chloride, if it does have oxygen, a lot of oxygen to it, I think it does. It oxidizes, corrodes, and the oxidation process is an electrical type of thing, but it's slow. It's slow. I don't know how you could speed up the oxidation process. It would be amazing to see that, though. If someone can come up with a chemical solution, you just put 1 drop in the water, and the oxidation process is sped up by 1,000 times, and the plate covers in it gets oxidized in front of you within a minute. And yeah, that's a possibility. It would be a very risky reaction to be around, I would think. What about nitroglycerin, like a diluted form of nitrogen, and in the solution? Would that speed up the oxidation? I would think so. It's highly reactive, but then you got to pay for the nitrogen. See, the goal here is to be able to use a signal frequency and to have hopes that some magic frequency will do this for you, so you don't have to spend money on chemicals and waste time waiting for processes. And I think that is ultimately the end game with all advances in medicine, like the beep beep. I didn't say that. All advances in whatever, sciences and all that, and health and science and health and science and math or whatever you want to call it. If you can use electrolysis to do everything, or frequency, which is also electrolysis, it's still, you don't have to use constant DC to do electrolysis. You can do pulse DC to do electrolysis. So those people who are charging their cells, their GANs plates with batteries, like 1.5 volt batteries or whatever, why not switch that DC signal at a high frequency or something like that, or a low frequency, even a low frequency? The experiments have to be done, until they're done, there's no way to know. I still think the electrolysis is the way to do it, though, and I don't think you need amps to do it. I think you need frequency control, tuning. If you can hit the right signal across a piece of copper with DC or AC pulse or whatever frequency you want to use, you hit the right frequency across that material, it most likely will respond to the oxygen in the water solution or the air, or it'll respond to environmental factors at a different rate than it does normally, and you speed up the breakdown of the material, which which is probably how the copper that's probably how the carbon gets to the material, because the material breaks down and it releases carbon. Just like a piece of wood, when you burn a piece of wood down to charcoal, well, that's almost pure carbon right there. So that's the way I look at it, you know. It's a, but you don't want to break down the material in a way where you destroy it. You just want to create that layer, and only one layer then, you know. Let's say you succeed in electrolysis and you start generating nanocarbon at a high rate, but then you have no way to turn it off before the second layer forms. Oh, a whole new project. All right, I gotta go to sleep. It's been good talking. Maybe next time you get the microphone working, Stephen. And talk to you next time. Blessed. Good night.